Hi everyone. So previously we talked about the first law of thermodynamics, and I introduced you to the equation of Q minus W equals to delta U. Okay, and I actually mentioned that this equation is only applied to a closed system, and we like to call this equation the non-flow energy equation, the NFEE. Okay, then your next question will be then for open systems, how will you then treat the flow of energy, and how does the first law apply in an open system, right? So the open system is not very far off. Let's have a look at this particular example over here. Okay, so let's say the a particular fluid, okay, undergoes this entire system, okay, and as it flows in, it goes in, and heat is being supplied over here, and naturally the fluid gets heated up, right? And it gets heated up, it increases in its energy state, and then as it comes through here, this is actually a turbine and this is a heater. So as it goes through the turbine, it will push the blades, the turbine blades around, and thus do work. Okay, so the gas actually the fluid actually does work, and then it comes out, right? So if you want to draw the boundary, it is basically encircling this whole area, okay, and the mass flow is mass flow in here and mass flow out over here. So we call this in as 1, okay, out as 2. And what you actually do is you are not looking at initial to final. You see, this one is actually final minus initial, right? And now for steady flow energy equation, we call it SFEE. Steady flow energy equation, it will no longer be a initial and final. Rather, it will be a inlet and outlet comparison. Okay, and the terms that are involved are as such. First, you have the at the inlet side. So the left hand side is the inlet side. Okay, what is the potential energy at the inlet? That will be your mg and elevation Z in. Okay, and then you have another form of energy, that is your kinetic energy. Okay, half m, we used to call it half mv square, but because v is now used for volume, so we replace it with c, okay, for velocities. Okay, half mc square. And you will also have the enthalpy, okay, the enthalpy at the inlet. Okay, note that the enthalpy is U plus pressure times volume. Okay, this is Ke, this is Pe, right? And we have the heat into the system. Okay, heat supply or the heat transfer to the through the system, and equals to, so this is the inlet. Okay, these three are the energy terms at the inlet. What happens at the outlet? You have the potential energy as well, kinetic energy as well, and the enthalpy at the outlet. Okay, ended off with the work term over here. So this whole equation is your steady flow energy equation. Okay, and it's comparing between inlet and outlet. So if you look at this diagram again, it's basically saying that as it go in and comes out, what happens inside the system that causes the change between the in and the out. Okay, the kind of heat that is being transferred and the kind of work that is being done. Okay, and this is all explained under this single equation. Okay, it might look quite different from the closed system, but actually, if you look at this carefully, right, I always like to tell my students, this is an energy state at the inlet. Okay, I can call this, let's say I can call this E in, and this is actually an energy state at the outlet, right? So this is E out. If I manipulate it a bit, right, you see that Q minus W is equals to E out minus E in. Okay, so actually at the end of the day it's actually a similar form to the NFEE. Okay, and if you divide by mass on every term in the equation, okay, you will get GZ in plus half C in square plus small h in, so it's the specific enthalpy, plus your Q is also per kilogram, right, so becomes small q, equals to GZ out plus half C out square plus specific enthalpy out plus small letter w. So this is the SFEE at specific level, and this is the SFEE at the whole system level, including all the mass.